Structural Continuity of Innovation Across Three Industries and for Decades Part 1, number 1588, the 6th of April 2026, Gerald C. EclaireMD Foundation. Category: Scientific Methodology. Preface: Across for Decades and Three Industries, my work has followed a single scientific question: how does structure evolve under repeated loading conditions over time? This question connects portable computing 1982, I-based semiconductor chip design 1994, and viscoplast topology modeling for neuroscience systems 2010-2026. Although these fields appear unrelated, they share the same foundations: physics, system dynamics, nonlinear dynamic interactions, and cumulative structural change. My career never followed disciplinary boundaries, it followed structural truth. Whether designing a portable computer, optimizing electronics chip connectivity, or modeling chronic disease, I have always focused on how stress, energy, time, and path reshape a system's internal structure. My hemorrhagic stroke on June 21, 2025 did not interrupt this trajectory, it clarified it. This mortality event provided a direct biomedical demonstration of these theories and principles I had studied for 6 decades: long-term damage accumulation, nonlinear triggering conditions, irreversible deformation within a viscoplastic system, and a nonlinear geometric topology changes. Viewed through this lens, the continuity becomes unmistakable. 1980 to portable computing required whole system integration, 1990 for semiconductor AI required optimized connectivity networks. 2010 to 2026 biomedical research required applying math physics to organic structures. The systems differ, but the governing principles do not. Early systems thinking, portable computing. In 1982, I built the Pied Piper portable computer. At that time, the concept of mobile computing did not yet exist in practical form. Personal computers were designed as stationary machines. Integrating computational capability, power management, mechanical structure, and software into a portable device required understanding the entire system as a unified structure. The challenge was not simply technical implementation, the challenge was conceptual visualization. The system had to function under constraints involving energy consumption, thermal management, physical durability, and user interaction. Each component influenced the others. Mechanical structure affected thermal behavior, power limitations affected computational speed. Software architecture influenced hardware efficiency. This early work taught me that innovation often begins before technology is ready. A good example is my concept of a chat-like linguistic AI system in 1983, which was 41 years ahead of its time. The scientist or engineer must first identify structural feasibility before implementation becomes possible. The Pied Piper project required systems thinking, meaning the ability to understand interactions among multiple components simultaneously rather than solving isolated problems. This structural mindset became the foundation of my later work. Mobile computing did not exist in 1982, but I was already solving a systems integration problem a decade before the industry caught up. This was a form of structural foresight. Neural connectivity and semiconductor AI design. In 1994, I developed an AI-based electronic design automation EDA tool that optimized chip layout and signal routing. Although artificial intelligence was not widely popular at that time, the structural idea was already evident. Complex system functionality emerges from optimized connectivity networks. Semiconductor chip design involves placing millions of transistors and connecting them through millions of electrical wires. The routing problem resembles billions of neural pathways among billions of neurons in the human brain. Signals must travel through networks efficiently, minimizing delay and energy loss while maintaining stable performance. Through this work, I began to recognize parallels between artificial high-tech systems and real-life biomedical systems, neural networks in the brain, circuit pathways in semiconductor chips, and algorithmic optimization structures share similar topological properties. Nodes, connections, signal pathways, and energy efficiency form the basis of intelligence in both the natural intelligence of the human brain and the artificial intelligence of computers. This realization strengthened my belief that structural principles can transfer across domains. Once a governing structure is identified, it can often be applied to multiple disciplines. The applications may differ, but the underlying logic and structures are identical, or at least highly similar. Transition toward biomedical system modeling. Beginning around 2010, I shifted my attention toward medicine. However, my approach to biomedical problems differed from traditional statistical frameworks commonly used in medical research. Instead of focusing primarily on correlation and population averages, I applied deterministic reasoning and a quantitative approach derived from physics and engineering mechanics. In mechanical engineering, structural materials experience stress, strain, fatigue, and eventual failure when subjected to repeated loading conditions. Damage accumulates gradually, often without obvious symptoms until a threshold is reached. When that threshold is exceeded, sudden failure occurs. Chronic diseases show very similar characteristics. Diabetes, cardiovascular disease, kidney disease, stroke, and dementia develop through long-term pathophysiological stress and accumulation of damage. The human body responds dynamically to metabolic inputs such as glucose, blood pressure, lipids, lifestyle behavior, food and nutrition, sleep patterns, and physical activities. Over 17 years, I collected more than 4 million data points from my own pathophysiological measurements. These longitudinal data allowed observation of patterns that cannot be detected through occasional clinical visits, rather than treating disease as a discrete event similar to viewing a still photo. I began interpreting disease as a progressive structural transformation of a biological system, similar to watching a movie. A good example is my recent stroke, which resulted from cerebral microvascular calcification caused by 3.6 decades of diabetes, combined with an episode of acute hypertension at 175 mmHg on June 21, 2025. This stroke scenario is similar to observing a bridge weakened by decades of heavy truck traffic that ultimately collapses when struck by an earthquake. This led me to apply concepts from viscoplastopology, a branch of math physics and engineering mechanics that studies materials exhibiting time and path-dependent irreversible deformations. Biological tissues and organs behave differently from inorganic materials, such as steel or aluminum. They adapt, repair partially, and deteriorate gradually. Mechanical properties evolve continuously due to metabolic conditions, inflammation, aging, genetic factors, and environmental influences. Therefore, the biomedical system can be described as a dynamic viscoelastic, viscoplastic, and topological structure. Organic versus inorganic structural behavior. One important realization from my medical research is the difference between inorganic engineering materials and organic biological materials. Inorganic materials typically have stable constitutive relationships. Stress-strain curves remain relatively predictable under controlled conditions. Biological tissues and organs behave differently. Cellular structures remodel themselves continuously. Blood vessels stiffen due to calcification. Metabolic imbalance alters tissue elasticity. Chronic inflammation changes mechanical response properties. The same level of mechanical stress can produce very different biological outcomes depending on the condition of the tissue at a particular time. For example, enlargement of the left ventricle in heart disease can be analyzed mechanically as expansion of a pressure vessel. According to classical mechanics, Laplace's law, increasing chamber radius increases wall stress. Reducing chamber size may theoretically reduce wall stress and improve pumping efficiency. Although biological remodeling effects also influence the long-term outcome, nevertheless, biological tissue introduces additional complexity beyond classical engineering mechanics. This mechanical reasoning influenced surgical procedures such as the Batista operation, where a portion of the enlarged ventricle is removed. I learned this concept from watching Japanese medical drama episodes and from AI-assisted searches of surgical information. However, biological tissue continues to remodel after surgery. Cellular behavior, vascular blood supply, and biochemical signaling influence long-term outcomes. Therefore, mechanical reasoning must be extended to incorporate biological adaptation. This insight supports the use of viscoplastopology VPT modeling concepts for chronic disease progression. This is part 1.